Aloha! In response to rising job market demands, many institutions have launched data science and machine learning programs. While these programs undoubtedly provide students with exciting new opportunities, several underlying issues raise concerns about the direction and effectiveness of DSML education. 1. Overemphasis on a single tool, the hammer-nail problem and baby duck syndrome. There's a well-known Chinese idiom: if you want to accomplish the best result, the priority is to acquire the sharpest tool. However, a counter-warning exists in the English idiom: when you have a hammer, every problem looks like a nail. Analysts should adapt tools to problems, not the other way around. Yet, in many data science programs, Python has been elevated as the only tool worth teaching or using. While Python is undoubtedly powerful and versatile, such a singular focus fosters a dangerous imprinting effect on learners. Brody observed that many data scientists rely on the algorithms they learned, rather than exploring a range of tools best suited to their research questions. This narrow mindset runs counter to the exploratory spirit of data mining. The phenomenon resembles what Seebeck termed baby duck syndrome. It means that individuals imprint on their first exposure to a system, like baby ducks following their parents. Just as many users imprint on either Windows or Mac operating systems and struggle to adapt to alternatives, students exposed solely to a single tool are less likely to explore other programming languages or analytic software apps. Educators must challenge this. By exposing students to a diverse toolkit, we promote intellectual flexibility, encouraging them to think critically about which tool fits the problem at hand, rather than defaulting to Python or R as a universal solution. 2. Conflating coding skills with data analytics goals. Coding is essential, but it is only a means to an end, extracting meaningful insights from data. Unfortunately, many DSML programs shift the emphasis from the ends to the means. Students often find themselves preoccupied with mastering syntax, debugging errors, and chasing technical minutiae, while losing sight of the bigger picture, solving real-world problems and answering critical research questions. This phenomenon is analogous to enrolling in a philosophy course and spending 70% of your time learning German or French. Similarly, a theology student who wants to study the Bible found that much of her time and resources is devoted to learning Greek and Hebrew. While coding remains an important skill, modern tools are transforming how we interact with data. Someone argued that coding is no longer a hindrance because AI-enabled code pilots can assist students to write and debug programs. However, while we ask AI to assist us to write programs to analyze data, is it better to directly ask AI to assist us to perform data analysis? Why is it necessary to add an extra layer? Should we try to get the answer using the most efficient way? I'm not suggesting we eliminate coding entirely. My point is, if you can accomplish the same task in minutes using drag and drop or prompts, why spend an hour coding it? This is exactly why we move away from DOS and IBM TSO to Graphical User Interface, GUI. Indeed, the rise of low-code and no-code platforms, combined with generative AI, is a game-changer. A Gartner report estimates that by 2025, 70% of new applications will use low-code or no-code technologies, up from just 25% in 2020. These platforms, with intuitive drag-and-drop interfaces, enable even non-programmers to perform complex analyses efficiently. Likewise, generative AI tools like ChatGPT, Google Gemini, and Claude can accept natural language prompts to analyze large datasets, identify patterns, and generate actionable insights, democratizing data analysis and making it accessible to all. The critical question for educators is, why force students to spend hours coding tasks that could be accomplished in minutes with user-friendly tools? Teaching the concepts of analytics, how to ask the right questions, design solutions, and interpret results, is far more valuable than teaching coding for coding's sake. 3. Failure to embrace the paradigm shift in data science. Despite its revolutionary potential, Some educators treat data science and machine learning as little more than traditional statistics on steroids. For example, linear regression is presented as the quintessential data science method in many DSML curricula, but indeed it is a classical method. Moreover, many people are still preoccupied with concepts like statistical significance. Such approaches miss the point. Data science represents a fundamental shift in how we understand and interact with data. Traditional frequentist statistics are limited by rigid assumptions and dichotomous decision-making. For example, reject or fail to reject hypotheses based on an arbitrary p-value threshold. In contrast, modern DSML methods break free from these constraints. Pattern seeking versus dichotomous conclusions. Instead of fixating on single hypotheses, data scientists identify complex patterns within massive datasets. Exploratory analysis over confirmatory testing. Hypothesis testing gives way to open-ended data exploration. Ensemble methods over one-shot analyzers. Techniques like bagging, boosting, and stacking provide robust results by combining multiple models. Embracing uncertainty. DSML acknowledges variability and avoids fixating on a single true parameter. Big data and multiple sources. Analysts now leverage diverse datasets, for example, sensor data, transactional logs, and social media streams, rather than relying solely on small, self-reported samples. Educators must ensure that students understand these distinctions and recognize data science as a new paradigm. This means fostering adaptability, creativity, and critical thinking, preparing learners not just to use DSML tools but to push the boundaries of what those tools can achieve. For data science education to remain relevant and effective, educators must address these three critical issues. 1. Teach a diverse toolkit. Python is powerful, but students should explore other tools. 2. Refocus on outcomes, not processes. Coding skills are valuable, but they must serve the ultimate goal, extracting insights to solve real-world problems. 3. Embrace and explain the new paradigm. Data science is not statistics 2.0. Programs must teach the revolutionary methods and mindsets that define modern DSML. The field of data science is dynamic and rapidly evolving. By equipping students with flexibility, conceptual clarity, and forward-thinking skills, we ensure they are not just competent workers but visionary problem solvers ready to shape the future. Thank you for watching.